Welcome to Energy Talks, a regular podcast series with expert discussions on power system testing topics. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Hello, everyone. In this episode, we will learn about how partial discharge, or PD, measurements performed in the ultra-high frequency range can be a reliable complementary or alternative approach to PD detection in noisy on-site testing environments. Here's some background information about this topic. The conventional method for PD measurement according to the IEC 6270 standard allows a precise calibration, but requires a sufficiently high signal-to-noise ratio, also known as SNR, in the measurement circuit. This is, however, very difficult to obtain on-site. External noise often presents a challenge when performing PD measurements during field testing, whether for on-site commissioning or troubleshooting. PD testing in the ultra-high frequency range, also known as UHF, offers a reliable completion or alternative solution to conventional PD testing according to the IEC 6270 standard. In this episode of Energy Talks, my guest is OMICRON PD application expert Ulrike Broniecki. She will discuss how UHF PD measurements can help you obtain a better measurement signal-to-noise ratio for reliable insulation condition assessment and defect detection in noisy testing environments. Ulrike was a guest expert in Energy Talks episode number 15 about AC and DC partial discharge testing, and I am pleased to have her back for this episode. Hello, Ulrike. Welcome back to Energy Talks.
Hi, Scott. Thank you for inviting me back into the podcast. It's always a pleasure to talk to you.
Well, it's always a pleasure to talk with you as well. Thank you. Ulrike, could you describe again why partial discharge measurement is so important and why this should be done on site?
Well, PD, or partial discharge, measurement is the most common non-destructive method for detecting insulation defects in electrical insulation systems. It's a very sensitive measurement, and it allows to draw conclusions about actual condition of the insulation system, and it enables detection and localization of critical dielectric defects. So you can guess why we want to know about those defects. On-site PD measurement is an important tool for quality assurance after the final assembly and installation on-site, as most of the parts are actually tested at the factory, but there is some amendments and some final assembly on-site, and we want to make sure that everything is working perfectly. Also, for the assets that have been in service for some time, on-site PD measurement is a useful tool as it helps assessing the aged insulation, and it helps us to move from a time-based to a condition-based maintenance plan, for instance.
Ulrike, what are the biggest measurement challenges on site?
Well, the biggest challenge is to maintain a sensitivity which is actually meaningful. Which is comparable to the sensitivity we are used to having at routine tests, for instance. And this is a challenge because doing on-site measurements, there are a lot of external disturbances. And these external disturbances can lead to the fact that the widely applied standards, such as the IEC 6270, is no longer useful to detecting weaknesses in the insulation or problems. And usually we cannot do a lot of the tools we have in the factory or in the lab, we cannot use on site.
Okay. Ulrike, do you have any specific tips to give our listeners about on-site PD testing in noisy testing environments?
I think the biggest tip is to combine different methods. If we have the PD measurement as we do it by the standard, this is one thing, but as said before, we have a problem with all of the noise there, and we have very, very many disturbances. So if we can combine methods, and maybe we can talk about this a little bit later, what kind of method this could be, we could gain more reliability on what we're measuring. And also, of course, we can use different software tools we're having. For instance, if we have a multispectral PD measurement, or if we can measure simultaneously at different locations, for instance. So this is really something that helps a lot to get some meaningful results, or to get some insight, even though we have a lot of disturbances.
How is noise typically dealt with during conventional partial discharge measurements according to the IEC 60270 standard? Are there specific tools or methodologies for minimizing the effect of external noise?
Well, yes, we have a lot of tools we are using for the conventional part, especially if we are in a lab or in a factory. For instance, we can do shielding against disturbances, so we can use a cage, for instance. We can filter. So there are different kinds of filters, but we can use a filter between the high voltage source and our device under test, for instance, that will reduce the disturbances we get through this part. And of course, we could also do filters in the low voltage supply, for instance, if we're really having a factory or testing in a factory. We can adapt, for instance, the measurement frequency also in the 60 to 70 to range where we can avoid some of those disturbances. Additionally, there are different techniques for gating, for instance, so we can use additional sensors and we can gate disturbances. We can use synchronous measurements at different locations and also use this for gating, for instance. If all of this really is not working, then we have to look for alternative measures.
Ulrike, why are these types of PD measurements termed conventional? There are also unconventional or alternative PD measurement methods. How are these measurement methods different, and when do you know when to use one over the other?
Okay, so how we distinguish between conventional and non-conventional methods is mostly down to the physical characteristics of detecting the PD. So what we usually call conventional is when for decoupling of the PD signal, we are using a capacitive sensor, like a coupling capacitor or like the capacitive grading of a bushing and using the bushing's measurement tab. So these are the measurement circuits as described in the IEC 60 to 70. So the standard that is dealing with PD measurement in general. So most of the time, we really say everything that is according to this standard, the IEC 60 to 70, all of this we call conventional. And then there are alternative methods for PD measurements, and these are mostly using different physical characteristics. For instance, we are measuring in a higher frequency range, or we are looking for the optical signal because the APD is producing a lot of different signals. We can use the acoustic method, so we could look for the noise APD is making. We have chemical PD detection methods, kind of, because PD is also producing chemical byproducts. Mm-hmm. So everything, and there's also some more electric measurement methods. For instance, if we're using capacitive coupling, but with very, very small capacities that are not covered by the IEC 60 to 70. Also, this could be described as non-conventional. And when to use? Well, Mostly, it makes absolutely sense to combine those methods, because the conventional method is for sure the most reliable, or the most used, and the one we know most about. And so it's kind of the most reliable method, and it's also very sensitive. But if we're facing a lot of disturbances, a lot of noise, and so on, all the other methods, when we use them additionally, they can help us decide if we're really talking about PD or about different phenomena. The conventional method, as I said, is described in the standard relating to PD measurement, the IEC 60-70.
One type of unconventional PD measurement focuses on measuring PD activity in the ultra-high frequency, or UHF range. Why is this a benefit in noisy testing environments?
Well, first of all, the UHF sensors are often installed in an enclosed asset, which has an enclosure, and this housing works a little bit like the cage, the shielding cage I talked before, as one of the methods to reduce noise. One other thing is that disturbances in the UHF range are often very narrow band or quite low ranged and well defined, like, for instance, radio frequencies or TV or mobile phones or radar. And so it's easier to avoid because they are not as broadband. So we can, while adapting the measurement frequency, we can avoid those disturbances. But there is a downside, or let's say there's two sides to this. The very high frequency range can limit the observable area due to the low pass characteristics of the propagation path of the PD. So we are very with UHF measurement, we are very sensitive to a very localized area, which is good because we are looking exactly at what we want to look. So by this, we are reducing external disturbances. But on the other hand, we only see problems or defects in the insulation that are really at the point or very close to the point we are looking at.
Ulrike, are UHF PD measurements beneficial on only certain types of electrical equipment when measuring PD activity in them? If so, what are these equipment types?
They are very beneficial for those types of equipment that have an enclosure. For instance, they are very commonly used in gas-insulated switchgear, or GIS, and GIL, gas-insulated lines. A second field of operation is the oilfield transformers, because there also you have a housing, the transformer tank, which acts as a shielding cage. And there is one third option that is quite commonly used as well, and that is high voltage power cable terminations. But for all of these, we require UHF sensors, which most of the time need to be installed permanently.
Interesting. Okay. Why are on-site UHF PD measurements often recommended for these equipment types? Is this setup somehow affected more by external noise?
Let's say for the first asset I mentioned, the GIS, this is a very big asset, and then there needs to be, it's usually transported in parts on site, and it needs to be assembled on site. So definitely we have to do a commissioning and an acceptance test on site, and to find any problems that are still present after the assembly. And as we said before, for the on-site conditions, it's very hard to do it with the conventional method. One thing is that for the conventional method, we need a coupling capacitor. And this is very bulky and heavy, and it's expensive to move, and we would need to include it in this enclosed area of the GIS. So we need to open it, we need to attach the coupling capacitor, we need to do our acceptance test, and afterwards we need to remove the coupling capacitor. So we need to open the whole system again and do some gas works, for instance, and then close it again. And then we again have the problem that we tested an asset which we touched again afterwards, and we did some things to it. So this is something actually we would want to avoid if possible. And for this, UHF measurement is a very, very nice way around this problem, because we don't need to open the GIS anymore after testing. And from experience, we have a long years of experience with UHF measurement in GIS. We know that it's sensitive enough to find problems if there are any. This is really like one of the main parts where we really have UHF PD testing very commonly. For the other ones, it's more an additional way of testing, I would say.
Mm-hmm. How are these UHF PD measurements performed? Now you mentioned the need for a permanently installed sensor is the best way. Could you describe further how the measurements are performed?
Yes, let's talk about the GIS first again. So for the GIS, you have to have the best possibility or the best result you will get if you have the pre-installed sensors. They are for all the newer GIS modules and designs. They're usually planned already, and they are installed permanently already from the manufacturer itself. Of course, there is some sensors you could use at the GIS externally, but they don't give as sensitive results as the permanently installed sensors do. So it very much recommended to use those permanently installed sensors. We have to use a measurement instrument capable of measuring the PD, for instance, the UHF 800, which will be then connected to the sensor. It's again, in the case of the UHF 800, again, it's a battery-driven measurement instrument, so we only need to connect it to the sensor, and we need to connect it to our computer. Then we have to look at the frequency spectrum. And so we need to do a frequency sweep, so sweep through all the measurement frequency range to have a feeling where we have those disturbances. Because we will have areas where we will have disturbances. Yeah, as I talked before, like mobile phone frequencies, TV, and so on. So we can have a look in which frequency range we can have the measurement and avoid those external disturbances. Or, as the other alternative, we can just use a measurement instrument that is measuring very broadband, so more or less all the frequency area of the UHF instrument, and then rely on the natural shielding of the enclosure. It's a little bit simpler because we don't need to decide on which measurement frequency and which band to use, and we are very sure that we don't miss anything. The next step would be to check for the sensitivity. Usually especially with the GIS and the UHF measurement, we have already in the factory, we have to start a sensitivity check where we install really a PD source and a coupling capacitor and a UHF sensor. And we're checking which level of PD measured with the conventional method. So coupling capacitor and according to IEC 60 to 70. and compare this with the result we get at our UHF sensor. Now, because the UHF sensor, the result will be in volts, microvolts, millivolts, whatever, and not in coulombs as we would get from the conventional method. So we need to make some connection, and this connection is usually very close to, or it's down to the exact line of the switchgear.
Okay.
And as a next step, we can then inject some with a calibrator a known charge, and then we can see where we can place our sensors to still see the defect on all the sensors, or wherever, no, let's say different, wherever the defect would be in the GIS, there's at least one, better two sensors who can still pick it up. But
Okay.
this really needs to be done in the factory before we go on site. But if we're on site, the best would be we have the results of the sensitivity check, but at least what we should do should be like more or less like repeating that final test. We should inject some source from a calibrator. We should inject some signal and make sure that we're really seeing it on the sensors, at least on the next sensor. And so we can get a feeling that we're really covering the whole GIS, and then we can start the general PD measurement procedure as we know it. So
very good. And is that the same procedure that you would use for oil field power transformers and high voltage power cable terminations?
Most of the things are very similar. So also for the oil field power transformers and cable terminations, we either need to have pre-installed sensors or we need to install the sensors. Usually at the power transformer, it's a little bit similar to the GIS. Yeah, if you open the GIS, you have it filled with gas, and of course, if you open it just like that, the gas will go out. So it's a little bit complicated, and with the transformer, it's a little bit similar because this is oil filled, obviously.
Sure.
So you also need to take care about that. So it would be better to have pre-installed sensors actually with that one. For the high voltage cable terminations, we usually don't have the problem, but we need to install it. We don't have a leakage problem, but we need to install the sensors.
Okay.
Then we have the same procedure, more or less, to check the measurement frequency range. For instance, like again, sweep through the frequencies, check for areas where to measure, or use a broadband measurement. But especially for the cable terminations and also for the transformers, usually it gives better results to have a medium band measurement to avoid really the disturbances.
And the on-site tests, are they performed generally online or offline?
Both, actually. Of course, we would prefer to do offline tests on site because it's much less external disturbances, it's much less noise, but
Sure.
It's very complicated in terms of logistics, in terms of transport, because you need to transport a high voltage source on site, which, of course, is logistics, which is a lot of work. You need to set it up, you need to connect it and so on, disconnect it afterwards. So that's why sometimes it's simply not possible to have an offline test. If this is not possible, we can of course always do an online test, but these online tests are, as I said, much more disturbances usually.
Okay. And of course, the online test would benefit from the fact that the sensors in that case would be permanently installed.
Yes, of course, if we have permanently installed sensors, we can just simply go there, connect without taking the asset offline, which is very, very important for a lot of the installations that we do not need to take it out of service. So if they have the permanently installed sensors, we just go there, we connect with the UHF, it's really not a problem to connect there while the asset is in service, and do our measurements and go home again. So it's really a great benefit.
So it's really just a plug and play situation.
Yes, yeah, right. Usually you have especially at the GIS, you have the sensors, there's a cap, you need to remove a cap, you need to apply your measurement system, your UHF 800, for instance, and you're ready to go.
Okay. Are UHF PD measurement systems different from conventional PD measurement systems?
Well, the main difference, of course, is the sensor and how we pick up the PD signal. And with that comes also that the frequency range in which we're measuring is different in both cases. Yeah, so for the UHF, as the name already states, we have the ultra high frequency range, usually up to 2 gigahertz, where we're picking up the PD, whereas with the conventional method, we're usually measuring in the kilohertz to megahertz range, where we pick up our signal. Apart from that, it's really quite similar from if you, for instance, take the MPD 800 and take the UHF 800. The main difference really is the different frequency range that they are working in, as I said before. And the UHF has this sweeping capability to automatically go through all the frequency range and give you this frequency sweep as a result. But apart from that, it's both are battery driven. So both you can power by battery, both talk to the computer via a fiber optic connection. So in both cases, you can place the measurement unit quite close to the sensor, quite close to your asset, and have the computer and have the operator at a distance, at a safe distance for the measurement. And also the software features we can use afterwards are quite similar, actually. So with both, we have the PIPD patterns, for instance, where we can look like those phase resolved PD patterns that we can use for analyzing the PD source. For both, we can adjust the measurement frequency if we're not using a broadband measurement with the UHF. For both, we can, for instance, use the gating as a noise suppression technique, for instance. So in the software, they really work very similar. And also, if we have the sensors in the GIS, we also really similar to the conventional PD measurement. Of course, we can do this as a diagnostic measurement, but we can also do this as a long-term measurement. We can use it offline, we can use it online. So all of this, very comparable, actually.
Okay. Very good. Can these different PD measurement systems, even though they're very similar, be used together? And if so, when does it make sense to do this? And how can this make PD testing even more thorough?
Yes, they can, of course, they can be used together. And it's really actually very beneficial if you have the chance to use them together. I mean, in some cases, we said we are using the UHF technique because we can actually not measure in the conventional way. But in a lot of other cases, we can combine the conventional method and the UHF method, especially, for instance, in power transformers. Where we have might have the measurement at the bushing tap adapters, and additionally, we might have a UHF sensor installed in the transformer. And this will always give us additional information, because we can, just to state it very, very bluntly, if we pick up a signal with a lot of different PD measurement techniques, let's say, we can be pretty sure that it's really a PD. But for instance, if we pick up signals that are most probably noise, sometimes we just pick it up on one of the sensors. And for instance, for this noise that can disturb our UHF measurement, those high frequency noise, as said before, like the mobile phone, like the radio, like TV, whatever, we won't pick it up with the conventional method, and vice versa, and because they are working differently when picking up the PD signal. And also especially for the power transformers, it's one other thing we can do, and which is very valuable, is, for instance, to combine the UHF measurement method with the acoustic PD measurement.
Interesting. Mm-hmm.
So for instance, we can use the UHF method for a trigger for the acoustic measurement, and the acoustic measurement we later can use for localization, for instance. But again, it's the same here. We have two different methods of picking up a PD signal, and if we pick it up really with both the methods, we can be reasonably sure that it really is PD. So yeah, wherever we are able to combine these two methods, it's really a great benefit.
Okay, very good. Ulrike, where can our listeners get more information at Omicron about partial discharge testing in the ultra-high frequency or UHF range?
Well, you can start by having a look at our webpage, OMICRONenergy.com, under applications, or you can visit some of our webinars, attend Omicron Academy courses. Of course, you can also ask us for a tailored course or a tailored webinar if you are interested in specific questions. Mm-hmm. For instance, UHF measurement specifically. You can visit us, of course, and talk to us directly when we're at an exhibition at the SIGWE in Paris, or at some IEEE TND in the US, for example. So, yeah, wherever you get in contact with us, we're happy to answer any questions you might have.
Great. Ulrike, thank you. Thank you very much for joining us for this discussion about UHF PD testing and how it relates to conventional PD testing. It was very interesting.
Yeah, it's been really nice to talk about this and the opportunity to explain some more about the different possibilities of PD testing. I really enjoyed it.
Great. Well, thank you again for being here with us. And a big thank you to our audience for listening to this episode of Energy Talks. We would really like to know what you think about our podcast and which topics you would like to hear more about in the future. Also, if you have questions about a particular episode for our guest experts, please let us know. To do this, simply send us an email to podcast@OMICRONenergy.com. We greatly appreciate your questions and feedback. Omicron has several years of experience in power system testing and offers you the matching solution for your application. This includes powerful conventional and unconventional or alternative solutions for partial discharge testing and monitoring. For more information, be sure to visit our website at OMICRONenergy.com. Don't forget to look under training for information about upcoming Omicron Academy webinars and courses about power system testing. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.